Hello, I'm Dr. Bettina Heinz, back again to teach you something about chemistry. We are now in episode 2 of matter, the topic matter, and we are going to do still a little carryover from the last episode, and mainly dealing with the pure substances and the mixtures. The mixtures can be subdivided into homogeneous and heterogeneous. Some people pronounce it homogeneous or heterogeneous. So both is correct. Let's look here and see what we have here on the platform. We have 3 Petri dishes that contain 3 individual substances or materials. Which of these 3 is a pure chemical? Now, for a chemist, it's very difficult to discern. One has to do analysis first to find out whether something is a pure chemical or a mixture of chemicals. Now here we have a pure chemical, which is copper sulfate pentahydrate, a beautiful blue crystalline substance. And here we have, let me take another spatula, a nice pure chemical. Now I know this already. This is boric acid. The formula H3BO3. And here we have, oops, I shouldn't mix chemicals yet. Here we have sand. Now sand looks pretty pure and uniform, but it is a mixture of various materials. It's usually silicates and polymeric oxides of potassium oxide, silicon oxide, and sodium oxide, and of course aluminum oxide. Then there are a lot of other things involved here, little mineral components, dust, little sand particles or dirt particles, whatever that may be. So it is a mixture. I know sand is a mixture because it's known to be a mixture. But theoretically, one would have to analyze the material. Now I'm going to do a mixture here. Just put them all together. And mix it thoroughly. So we have a nice mixture in the end. And then I'm not going to separate these chemicals here in the show, but I will show you the flow chart needed to isolate these individual chemicals again. We have to use a chemical or physical workup procedure in order to isolate these components out of the mixture back again. So we'll learn about that later, and I will go on and cover the topics that we have planned for today. Separation techniques, as I already mentioned, are very important to isolate chemicals out of their mixtures, and most chemicals in nature are associated with other chemicals. And of course, technically, many of our commercial products are also mixtures, but these are man-made mixtures. That means they have a certain purpose to be in such a mixture. We're going to talk about physical and chemical properties and reactants, the chemical change, and the law of conservation of mass, which is was originally found out or discovered by Lavoisier in France in the 18th century. So the chemical equation and what it means for us. Now first let's look at the mixtures again. There we go. Now mixtures, as I already mentioned, are a conglomeration of pure chemicals. Often you cannot tell whether something is a mixture or not, so therefore we have to work up the chemical and apply certain separation procedures to get the components in their pure form again. Now, depending on how the chemicals are mixed, whether we can see with the naked eye, whether there are different phases or whether the phase is uniform throughout. A phase is always something that we can discern with the naked eye, usually. That means we have a different type of matter that is seen as a separate phase. So homogeneous or homogeneous mixtures are in our environment, in our food cupboard, for instance, in our refrigerator. And here we have a milk carton. Milk is a mixture of many chemicals, fats, water, proteins, minerals, vitamins, and often hormones, which are artificially put in there. So we have here an emulsion of two non-miscible liquids like water and oil. When they're finely shaken and finely dispersed as a result, you cannot tell the difference between the individual components. So it's a milky type of substance. Milkiness you also find in many hand lotions or cosmetics. They contain certain stabilizers or chemicals that keep the phases intermixed. And mayonnaise, for instance, also a mixture of egg yolk, eggs, and oils finely shaken up to make an emulsion. Only the consistency is a little different. So these would all be homogeneous types of mixtures. Heterogeneous mixtures are observable to the naked eye as being separate things. So if we see here this lady on the beach, what are mixtures around her environment? Well, the seawater, when you look at it, seems pretty uniform. If you would study it under a microscope, of course it would be quite heterogeneous, but with the naked eye it seems pretty homogeneous to us, unless there's a lot of seaweed floating around. And the sand, from a distance, looks homogeneous, but when you look close, you can see the fine little different particles. In a coarse sense, gravel would be obviously a heterogeneous mixture. That means you can actually pinpoint the individual particles and pick them out with tweezers, so to speak. That means you can see the difference, obviously. Let's look here at some orange juice. Now, many people don't like the pulp in the orange juice, so then it's considered pulp-free orange juice. That would be homogeneous. But if you like the pulp for roughage in your diet, then of course you have these little orange fruit flakes floating around in the liquid. So that is obviously a heterogeneous situation here. So the guideline is actually the naked human eye to distinguish whether something is homogeneous or heterogeneous. Because if you would use a microscope and produce more and more enlargements, then of course eventually you will see some phase differences. Now let's look at some separation techniques that are used in the laboratory. The simplest form is decantation, just pouring the water off the potato, so to speak. So it's a very crude technique, and when people hear about decantation, they think, oh, what is that? It sounds so technical, but it's actually really simple. If you have sand and water, you would decant, for instance, because the residue will remain nicely behind. Or if you just want a crude separation, then decantation is very good. Filtration is a little bit more advanced. That means we use a filter paper that we fold 2 times and put into a funnel. And we tear off the corner, and which makes it stick better to the glass. Then we slush up our mixture that will be separated. If we have a precipitate, for instance, and we want to separate the residue or the precipitate from its solvent, original solvent. Then we pour it through the funnel, and the bottom part would be the filtrate, and whatever is left in the filter paper is called the residue. Another technique to get rid of the solvent from the solute, or let's say we do not have a precipitate that we can easily filter out, then we can just evaporate the solvent. Let's say we got some salt water from the ocean or from the beach, and we put it in a little porcelain dish and add a steam bath to it so that the hot steam will heat the porcelain dish, which is heat resistant, and eventually the pure H2O will evaporate and leave a residue, a crusty white residue of all the minerals that would be involved in the seawater. So that way you can separate already some chemicals. This is a distillation apparatus. So glass is very important for the chemist in a historical sense and even today. Distillation is an extremely important method, and we have introduced it already as a little lab video in the introduction to this course. But here again we have the setup of the distillation apparatus. We have a round bottom flask which contains our solution. In the video we used potassium permanganate completely dissolved in water in a nice magenta colored solution. Put a few boiling stones in there to prevent bumping of the liquid as it heats. We have our heat source. This is not a Bunsen burner this time. This is a heating mantle. And so the solvent will eventually reach its boiling point, come across the three-way connecting tube, and will flow through the condenser that, with the help of a water mantle outside, without any contact to the inner tube, will cool the vapors back down so that they can condense as a liquid, and then we can collect the solvent on the other end in the so-called receiver. Now with evaporation we lost the gas or the vapors, but here we can recover them. So it's a recycling method. Also, you can make certain brews that you can collect on the other side. In potassium permanganate, here we have the formula, is KMnO4, and we separated it into the original crystals again, and the solvent, which is a liquid that appears on the other side. Now one should never distill too much, that we have a crust in the bottom of the flask, but we will allow the remaining liquid molecules to evaporate on their own without heat. So distillation can also be used for the separation of miscible liquids. However, there are some liquids that cannot be separated. These are called azeotropes. So one has to use some tricks to separate them out, like adding another chemical. Another important technique is extraction, and I will show you the mechanisms of this process and then illustrate that with a lab video. Extraction means that we selectively remove a chemical that is preferably soluble in one solvent, which has to be immiscible with the original solvent. So that means we will see a phase difference. You see the less dense liquid will be the top layer of the test tube here, and the bottom will be the more dense liquid. Notice when they're not miscible, like oil and water, we see a phase difference. So here we have iodine in an aqueous solution, water-based solution, and we add an organic solvent, hexane, to it, and we can see already some migration of the iodine molecules into the organic solvent. And if we agitate and shake, then the top layer will be more and more purple or magenta colored, and that means the iodine molecules migrated into the solvent in which they prefer to be housed. Like associates like, and iodine is a nonpolar molecule that likes to be more in nonpolar environments. And here we see a little cartoon that says that iodine prefers to be associated with the hexane molecules and not the water molecules, although it can be soluble in water. And now let's see that video so you can see things in action. Hello, welcome back to our lab. We will discuss another interesting separation technique today, and that is called extraction. That means you literally extract a chemical from one solvent and move it into another. This is a very valuable technique. It's used a lot in organic chemistry with separatory funnels, especially in isolating natural products from their sources, the plant material. But here we have a simple way of demonstrating this technique. We are going to use iodine solution, an aqueous iodine solution, meaning iodine dissolved in water, which makes, I'm going to pour it directly here into the big flask. And you see that it makes a beautiful amber-colored solution. So it's in a polar environment because water is a very polar solvent. But it's not completely happy here. It would be more happy in a non-polar solvent. In organic solvents such as hexane, carbon tetrachloride, benzene, chloroform, etc., etc. So these chemicals, these two solvent systems are not miscible with each other. So they make an interface. So they don't make a pure solution. You can see the little barrier where one liquid sits on top of the other. We call that a phase difference. And I'm going to add now hexane. Smells very organic. And I'm going to pour it onto this aqueous iodine solution already. I better stop this because the vapors are not very healthy. So we see here, nothing happened much yet, but you definitely see the beautiful interface. Now, which you think is the less dense liquid? Well, obviously the one that is on top, and that would be hexane. So hexane has obviously a lower density than water. Now that's a good proof. Now the iodine will start recognizing that liquid, and you can see a very, very faint pink coloration of the top layer. That means the iodine molecules are already migrating up into that portion of our test tube here. But I can help them along by agitating the solution, the two components, by shaking. And look what's happening. The top layer is getting into a nice pink coloration, and the bottom amber-colored liquid is getting paler or fainter. Well, we can understand that because the iodine is moving away. It's moving out of the water into the organic phase. And if I shake it more vigorously, you see the bottom is practically colorless. So all the iodine is now where it wants to be in the non-aqueous part of the surroundings. So all the iodine molecules moved into the top layer. Now I could use this further and use what we call a separatory funnel and isolate or pipette off the top layer here, and then let the solvent evaporate, and then I would have the iodine crystals back in my crystalline solid form. So that is the extraction method of isolating chemicals by moving them from one solvent into another. Now let's imagine iodine was with many other chemicals together in a heterogeneous or heterogeneous solution. Then I could selectively isolate iodine from its neighbors. And that is a purification technique. So isolation, extraction techniques, separation techniques, etc., are valuable methods to isolate certain chemicals and separate them from others. And in chemistry, that's what we usually want to do. We want to purify chemicals. We want to isolate them and then do research with them and study them and so forth. So most chemicals, as you remember, are in mixtures. And extraction is a valuable technique, as you have readily seen by my demonstration. In organic chemistry, this is used a lot, but we're not studying organic chemistry in this course. That would be interesting for a future course. See you next time. So, now we go back again to our three-component mixture here that I have on the screen, and we will look and see how we can separate these. And that means we will demonstrate a flow chart of how the procedure would be to get these three components back again, which is actually done in a lab situation. Now we have the mixture, so we would dissolve it first in water. And you know, of course, that sand does not dissolve in water. So we would have a residue of pure sand, and the two other chemicals, which are quite water soluble, copper sulfate and boric acid, will then be in the supernatant, which is the liquid above the residue. So we have a slush of sand. That means we can filter the sand off and isolate the sand on its own again. All we have to do is actually just dry it a bit, leave it out in the air for the water to evaporate, and then we got our pure, nice, clean sand. I can go back to the beach and put it back where I found it. Now on this side then we have the sand separated out. The technique that we used was dissolution, meaning dissolving in a solvent, which was water, and filtration. And in the filtrate, we have now pure copper sulfate and boric acid both dissolved. That's why we say in little parentheses AQ, coming from aqua, meaning water-based or water-dissolved, aqueous, in other words. Now we have to separate these two components from each other. What can we do here? Now there's an interesting chemical property of boric acid that its solubility decreases considerably in the cold. So it settles out when we put the flask that contains both of these chemicals in an ice bath. Copper sulfate will not precipitate out at that temperature, but boric acid would. So it has a lower solubility than copper sulfate at this temperature. This we can utilize selectively to trap boric acid and isolate it from the rest of the chemicals, in this case only being the copper sulfate. So we filter out and we can isolate then the boric acid. We have to make sure it doesn't warm up. And then we can have the boric acid on one side as a solid, and we only have the copper sulfate now left, but it's still in aqueous solution. So the next thing I can do is evaporate the solvent and have a residue of pure copper sulfate. So in the end, I have all three components in their pure form again. The only danger is if I heat the copper sulfate up too much, then the blue color would disappear. That means the hydrate water would come out of the crystal lattice, and that would make a colorless substance, which it is in reality. The hydrate water gives it that beautiful blue color. Now with this, I want to talk about one more separation technique, which is pretty common in science or chemistry, and that is chromatography, meaning writing in color. So we can use paper, we can use different support media. We have a mixture here that we apply on a paper strip in this example. So this is only a short introduction to that technique. And then we can place that paper that has to be adsorbent into a solvent mix, which we call the effluent or the eluting chemical mixture, liquid mixture. And then by capillary forces that creep up into the porous paper, or the as a result of the fine little channels and crevices in the paper, meaning its porosity, the liquid will drag the components upward and since chemical and physical interactions take place between the component or the solutes with the paper and the solvent system, we have, in the end, a different location of the components. The components are the chemicals that make up the mixture. In this case, we have colored components in the true sense of the chromatography idea, but in reality, many chemicals are not visible, and they have to be made visible by other means, such as UV light that would indicate maybe a fluorescent chemical, or we have to have special sprays that produce certain reactions of the chemicals that lead to a visible spotting. So these are excellent techniques for the resolution of chemical mixtures. We measure the distance traveled of the spot by the total distance of the solvent front. This is called the retention factor, and every chemical has its own retention factor, and you can identify unknown chemicals. So this is often used in the drug industry because the drugs have their own RF value when using a certain combination of materials. The forces involved, as I already mentioned, are capillary forces. So we would call this type of chromatography ascending, meaning climbing up, but we also have descending types of chromatography. Chromatography is such a big field now, and it's used in every sophisticated laboratory nowadays, especially in the form of HPLC, which is high pressure liquid chromatography, and gas chromatography, which is gas GC, as we call for short. And then we have, of course, the traditional types, paper. In the organic synthetic lab, TLC plates are used. That means paper is not the actual material. It's a plastic film that has been covered by a certain adsorbents, a powder which has a binder that makes sort of a paper-like situation. So this is a very good technique, also in the separation of chemicals. Now, I already mentioned that in the chemical sources around us, most things are mixtures. And this is what we call a scrapbook that students make, where they put in labels of various chemicals in the environment, like drugs, or medications rather, and food labels. And you see when we have the list, many, many chemicals are in here. Thank you very much, and see you next time.